Hi everybody, and welcome back to part 5 of Bravo project. If you have watched the previous video, we built this module, including the clock and program counter module. In the previous video, we went through the clock module. In this video, I'll be talking about the program counter. So with that, let's have a look at the logic behind the circuit, and then we're going to test this module.
All right, so let's have a look at the program counter circuit in our computer. As you may know, the program counter is basically a part of the computer that points to the next address of the memory that contains an instruction that needs to be executed. So essentially, it's a counter that with each count points to a specific program step, and that step will be fetched from memory and will be executed. So if you're one of those who have built the Ben Eater's 8-bit computer, you know that we had a 4-bit binary counter in that computer as our program counter. And that means that we could count from 0 to 15, and that means that we could have a maximum of 16 steps in our computer. Well, here we have a 16-bit binary counter, so that means that we could actually count from 0 all the way to 65,536 or 64K. So let's see how this 16-bit binary counter has been implemented here. So here we have actually quantity 4 of 74 HC161 chips. Each of these chips is a 4-bit binary counter with input and output. Now, when we cascade those chips together, using the carry-out and carry-in signals, then we could basically tie all of them together and make a 16-bit binary counter. Now let's focus on one of these chips and see how it works. So each chip has 4 inputs and 4 outputs. The inputs are from D0 to D3, and the outputs are from Q0 to Q3. So that means that we could input 4 bits, or basically any number between 0 and 15, into the chip. And also, we could have an output between 0 and 15. Now, let's focus on the inputs and also on the control signals. So the inputs only make sense when we actually have a jump instruction in the program. In a normal situation, when you turn on the computer, basically the counting starts from 0 and will just continue to count. However, if during the program execution you want to actually jump to a specific step in the program, then we're going to input some values on the input side, and basically that sets the counter at a specific value so that when it starts counting on the next clock pulse, it will be counting from that specific value. I guess that makes sense more when we get into testing the circuit, and I'm going to show you how this works. But for now, we're just going to have some inputs, and of course the outputs are going to show up on our output pins. Now this chip has a PE or parallel enable pin here, which is an active low pin. Whenever we want to read something from the bus as an input to the chip, we're going to bring that pin, which is pin number 9, and we're going to bring it low. And that only works when we actually have a input. We wanted to basically read something from the bus and input it as an input into the chip. That is normally tied to our counter in signal. Now we have 2 other pins, pin number 7 and pin number 10. Both of those pins needs to be set high for the chip to count. Pin number 7 is the count enable pin, which as you can see is tied to our count enable signal. And also number 10 is a carry in pin. On the first chip on the right hand side, as you can see, since this is the first chip and we basically have our least significant bit and our Q0, we actually tied both pin 10 and pin 7 together, and we're going to use only one signal, which is the counter enable, to enable counting. For the rest of the chips, pin number 10 is actually tied to a carry out of the previous chip. So let's see how it works. So let's say that we start a computer and it is basically reset to 0. And the first chip, as soon as it receives the basically clock pulse, and also we have the count enable high, then this chip will start counting. With each clock pulse, it counts 1, and it continues to counting. Now, once this chip reached a maximum of its count capacity, which is 4-bit up to here up to 15, then it's going to have a carry out signal on the carry out pin, which is pin number 15 on the screen. So this carry out signal goes to the next chip and now enable the counting on the next chip in the row. So meaning that until this chip has reached its maximum count capacity of 15, there will be no carry out signal, and therefore the next chip here will not be counting. So that means that basically by cascading those chips together, we would be able to count from 0 to the maximum number of counts that are possible when we're combining those bits together. Now, this chip obviously requires a clock to count, and as you can see, pin number 2 is the clock signal, which on all chips are tied to clock. We also have a reset pin number 1. This is an active low signal, and this is tied to our active low reset signal in the computer. So on the output side, you see that the outputs are going to Q0 to Q3, and those outputs all go to a transceiver. We are using a 74HC245 as a transceiver, which essentially enables us to store that output of the counter, and then when needed, it just output them on the bus. Now, let's talk about the transceiver a little bit. The transceiver is quite simple. It has 8 inputs and 8 outputs. You could actually select this the direction of the data to be from B side to the A side, or from A side to the B side using pin number 1. Pin number 1 is basically a pin that when you set it low, then the direction will be from B to A. If you set the pin to high, then the direction will be from A side to the B side. In this circuit, the direction is always from B to A, and that's why we actually set that pin too low. Other than that, we only have a single pin here, which is chip enable, pin number 19, that basically when you bring it low, that's an active low pin, then it puts the data on our output or on our bus here. So that's really all about the transceiver. Now, if you look at the circuit, you see an interesting thing. So as you can see on the screen, our counter is actually a 16-bit counter. However, our bus is still an 8-bit bus. So that means that we would not probably be able to write all the 16 bits at one shot on our bus, right? Therefore, we actually divided our program counter into 2 sections, which we call them low byte on the right-hand side and high byte on the left-hand side. And as you can see, the outputs of the first 2 chips on the right-hand side and the low byte goes to a single transceiver, while the outputs of the left-hand side also go to another transceiver. So that means that at each point of time, we'd be only outputting either the right-hand side or the left-hand side. As I mentioned, you could not write a 16-bit output of the program counter in 1 clock cycle on the bus. So essentially, you're going to need 2 clock cycles for that to happen. And that's why we have a concept of low byte and high byte when you're going from 16-bit to an 8-bit bus. Now, you may ask, could we just have the bus 16 bits? To be honest, it is possible, and you could just have a 16-bit counter and also a 16-bit bus. The only problem with that is that when you actually expand your bus to 16-bit, then you need to think about expanding everything else on the computer. For example, your A and B register also probably would need to be 16 bits, or your ALU should be a 16-bit ALU, and so on. So essentially, you are just need to expand probably everything in the computer. Otherwise, you always have that concept of high byte and low bytes, And basically, you need a sequence of 2 clock cycles to be able to get that information from a 16-bit, let's say, program counter to an 8-bit bus. So now let's see how it works. So if we actually want to write all these 16 bits as an output of our program counter into our bus, we need to divide the circuit in 2 parts, right? As we can see on the screen. And basically at each point of time, we are activating only half of that circuit, meaning that at first clock cycle, we'll be activating these 2 chips on the right-hand side, and we get the output of those, and we put it on the bus. Then we do something with that. We process that data on the bus. We either read it into our memory address register. We could probably input it into our register, or whatever you want to do. So once that operation is completed, then we're going to activate the circuit on the left-hand side, these 2 chips here, and then we're going to repeat the same process. So as you can see here, we probably need a control mechanism here to be able to enable the low byte side or high byte side at each point of time. And that has been implemented using an extra signal, which we call it HI, or high signal here. This signal is generated in our control logic, and we're going to look at it when we are actually building the control logic. However, when we are generating that HI signal, we also inverting it using a 74HC04 chip, which basically gives us the original signal and the inverted version of it. Now let's focus on the output side first. So let's say that we have a value in our program counter, and it's a 16-bit value, and we want to put that on our bus. Now, if you look at these transceivers here, they have, as I mentioned, pin 19, which we normally connect only the counter out signal to it, right? This is an active low signal. We just bring that line low, and that basically outputs the content of the transceiver on the bus. However, as you can see here, we are actually combining that counter out signal with a HI signal, or with the inverted HI signal. And we are feeding those into a 74HC00, which is basically a NAND gate. So let's see how it works. Let's say that we, at first step, we want to just output the low byte on the bus. So by default in our computer, the HI signal is low, meaning that we're not bringing in that high until we want to actually read or write to the high byte. So by default, the HI is low. Therefore, when it comes to our NAND gate, it's going to be low, and therefore, even if you have the counter out signal, the high bytes is not going to have an output. The output of the NAND gate is only low if both of the inputs are actually high. So as you can see here, we kind of deactivated the high byte. However, we have the inverted version of the signal, which is the inverted HI, and that is combined with the counter out signal, which is an active high signal, and both of those are coming to another gate on the 74HC00. So that means that the signal by default is high. If we bring out the counter out high, then we have 1 and 1s on the input of that NAND gate, and therefore we're going to have a low signal on the output, which means that we are enabling the low byte output. So by default, when we turn on the computer and we want to do the output, if we just bring up the counter out signal, we are actually outputting the low byte. Now, once that operation is completed, the only thing that we need to do is just bring the HI signal high. When we bring the HI signal high, the inverted HI will be low. Therefore, this side of the circuit will be disabled from an output perspective. And then the high byte side will be active because the HI will be high, the counter out will be high, and therefore the output of this NAND gate will be low, and therefore we have an output on the high byte side. Now, the same concept applies to the input side. We are actually combining the counter in signal with both HI and inverted HI, again through some NAND gates here. And as you can see, those NAND gates are going to pin number 9, which was, again, an active low pin for the input side. And if you look at the circuit on the right-hand side, you would see that the low byte signal are actually coming only to these chips on the low byte side, meaning that the pin 9s of those chips are tied together, and it all goes to the low byte side, which is the inverted HI. And the chips on the left-hand side are also, pin 9s are tied together, and that's actually going to the high byte side of the control circuit at the bottom. So this way, the end result is basically quite simple. By default, we are always reading and writing through low byte. However, as soon as we bring this HI signal high, then the low byte side will be disabled, and we'll be either inputting or outputting from the high byte side. Again, this is the whole really logic behind the program counter, and I hope it make a little bit sense. But we'll be testing this using our Arduino shield. So I guess when we are testing it, it makes more sense to look at how actually the high byte and low bytes works. So with that, let's go ahead and test the circuit and see how it works.
All right, I guess we are ready to test our program counter. Just before we start the process, there is a point that I would like to mention here, and this is about the clock module. Remember that we are not using this original clock module for the tests here. The reason being is that this is a clock that is running at really high speed. And during the testing, we will be using the clock from our Arduino shield. Therefore, we just disable this clock for now until we have a complete build, and then we could re-enable the clock. So in order to do that, you just have to make sure there is no jumper connecting those pins. Essentially, we don't have any output on the clock module. And I'm removing this jumper cap here. Well, I just connected to one pin here, just not to lose it, but otherwise I'm not shorting any pins here. So other than that, we are ready to go. So what I'm gonna do, I'm gonna mount this in our Arduino shield, and this is basically providing power to our module, and at the same time we could read and write to the signals. So let me just mount that. It's easier than that. All right, so that is our program counter, and also I will add our LED board to the build. The only thing is that as you may have noticed, we don't have actually dedicated LEDs for our program counter output lines. However, since the output are shown on our bus lines, we could always see the outputs on the bus lines and also the control signals. So let's mount the LED board also to the build, and we go from there. Okay, so I guess we are ready. We just need to connect our power, and we start the sketch. All right, so let's connect the power. All right, so I connected the power, and the first thing that you probably have noticed here is that all our bus lines are set to high, and it is normal because if you remember, when we were building the clock circuit, I explained that we have a resistor array there that actually tying all of our bus lines to high. So essentially, when you're not writing to the bus lines, all of them are set to high, and that's why those LEDs are already on. Now, we don't have any sketch right now loaded on the Arduino Mega, so we're gonna go ahead and have a look at the sketch and load it and see what will happen.
Okay, so I have loaded the program counter testing sketch. So we have a section here, which is, I just call it general functions, and this is basically part of the sketch that define the pins and also initialize the Arduino Mega Shield. I talked about this in the previous video when we were testing the LED board. So I guess we could just go ahead and start where the testing basically functions are for the program counter. Now, the program counter, we'll be testing two things here. First, we'll be testing just a counting operation, and basically we start counting, and we read the bus lines with each count, and we print them on the screen. So this has been done through a function called step program counter, and takes a variable as a parameter, and this is basically number of steps that needs to be counted. We also have another function here, which is the set program counter, and that basically set an initial value on the program counter. We're gonna look at that later, so let's comment that out for now. At the first step, we will be just testing the step counter itself. So let's have a look at the function. First of all, we're gonna have two delay timers here. One is basically a delay time for in between different control signals, and this has been included only for visualization purposes. So essentially, when we are running those control signals and we are going to bring them high or low, it's going to happen really fast, and we will not going to be see anything on the LEDs. That's why we could increase that numbers to, let's say, a second or so, and this way we'll be able to actually see the LEDs blinking on our LED board. So I'm going to set that now for 1000 milliseconds, which is equal to 1 second. And then we have another delay here, which is our clock delay. And this is essentially the length of the clock. And right now it's set to 10 milliseconds. We could increase that later when we are actually doing basically the set program and so on. But this is basically the time in between each clock pulse. Now, the pulse clock function itself is quite easy. Essentially, it's just, if you remember, I said that we actually designated pin number 2 as our clock out signal, and that's what we are doing here. Basically, we are just bringing that pin high, wait for a delay, and then just bring it low again. So essentially, this function is just generating a clock pulse each time that we call the function. All right, so we have another function here, which is the reset program counter. And what it does is basically just set everything to default. We are working with a couple of control signals here, and those control signals needs to be kind of set to default or initialized. So that's what we're doing here. For example, we set the clock pulse to low at the beginning. As you can see, the HI signal is set to low, while the inverted HI here is set to high. So that means that it is basically the default status of the system. But again, these HI and inverted HI are actually happening automatically once we build the hardware in our control logic. But here, since we don't have the control logic yet, we actually have to do it manually here through to our sketch. And then we have the counter enable. And by the way, don't get confused here. We have a counter enable, memory enable signal here. The reason for that is because we are using the same signal in both a program counter and also later in our memory module as the memory enable signal. So these signals are kind of combined as CEME, or count enable, memory enable. So this is essentially just the count enable for us here in this sketch. And then we have the counter in, counter out, and of course we have the reset signals. And if you look at the reset signals, I'm actually bringing it low for a second or for a moment, and then bring it high again, and that basically causes our program counter to reset to 0. Now, in regard to the sketch itself, as I said, we have a section called step program counter. Let's have a look at that. So this takes a variable as a parameter, as you can see here, and that basically is the number of steps to be counted by this sketch. So we use this variable in a for loop function here, down here, which basically tells how many loops it should take during the execution. Now, as you can see, the first thing that I'm doing here is enabling the counter out. I'm setting it at high, and also I'm enabling the count enable signal high. So that means that we want to actually output the content of the program counter onto the bus. However, if you go down, we are still needing another signal, which is the HI signal, and we're gonna basically do that inside the loop. So first, we're gonna define a couple of variables here, including the low byte and the high byte. which are basically just an integer holding the low byte value or high byte value during the for loop. We're just saving them into a variable so that we could print them on the screen. Now, we also defined a character array, and again, this is just basically to output the results of those integers on the screen. And finally, we have a data word, which I'm going to talk about that shortly in the for loop. So now, with the number of steps coming from the parameter, we create a for loop. And basically what we're doing is that we're going to read the low byte and then read the high byte. So first, focusing on the low byte, as you can see, I'm actually setting the inverted HI to high. And then I am basically bringing the HI signal itself low so that we are only enabling the low byte side of the circuit. What we're going to do is basically we're just going to call a function called read bus that I'm going to show you in a second, and that reads the value from the bus lines. And then we're going to wait for a short delay, and then we're going to go read the high bytes. So first, let's have a look at the read bus function. The read bus function is quite simple. It's just a simple function that goes through each of those pins in our Arduino that we have defined as our bus lines. If you remember from the top, we had those basically all the bus lines defined in an array, and these are the pins. So we are through a for loop, we are going through those pins and read the value essentially on all of those pins, and basically return that value to our main function. If you look at it, we have a digital read that reads the bus lines one by one, and if it is true, it assigns a value of 1, and if it is false, it assigns a value of 0. So now, if you look at this little for loop here, you see that I'm reading the value of each pin, and I'm basically adding it to a variable called data. And each time that I'm going through the loop, I'm actually shifting 1 bit to the left side. The reason for that being is that we are starting from the most significant bit on our bus lines. Essentially, when we read those, we wanted to shift them to the left and add the next bit to it, and so on. The end results will be just the value of bus line. All right, so with that, let's go back to our main function. So on our main function, as you can see, we have the section to read the low bytes and then the section to read the high bytes. And in the high byte section, the only thing that we do is just basically reversing those HI and inverted HI signals, meaning that this time we want actually the HI signal to be high so that we activate the circuit for the high byte side. And then again, we have a short delay here. And then finally, what we're doing is we're just printing those values that we read from bus for the low byte and the high byte on the screen. So this section just prints those values on the screen, as you can see. But again, we also want to have that output somehow formatted on the screen. So that's why what I'm doing here is that first I define a data word variable essentially as an integer. And what I'm doing is that I'm multiplying the high byte by 256 so that it actually shows the high byte value, right? So if you think about it, the high byte actually needs to be multiplied by 256 if you want to add it to the low byte and have an equivalent of a 16-bit integer number. So I'm just creating a word here, essentially combining the low bytes and the high bytes to have a full word here. Now, what we're doing in the next line is just the using the output variable that we defined at the top to show those numbers on the screen. And basically, first we're going to show it as a hex number on the screen with a maximum character of 4, and then we're going to show the same number in a decimal format. And as you can see, I'm fitting again the same number to both outputs. And finally, we're going to print that output on the screen, and we're going to pulse the clock. So that means that when we actually going through the for loop, we're going to read the high byte, read the low bytes, combine those, print them on the screen, and then finally pulse the clock. And when we are pulsing the clock, the counter will be counting to the next number, and we're going to repeat the same process here. So that is the step program counter function. So let's execute that and see the results on the screen. All right, so let's check our sketch one more time. And then we're going to upload that to our Arduino. And now I'm going to open the serial monitor. All right, so what we see on the screen is basically the output of our program counter on the bus. What we're doing is just reading the bus values, basically first the low bytes, and then we read the high bytes and we print them on the screen. So this is basically, this side is the low byte side, and then we have the from basically here to here is the high byte side. Now, as you can see, I'm also converting those basically to hex, and then the decimal value also is printed right in front of it. So as you can see, the program counter is actually start counting from 0, and with each clock pulse, we are incrementing the step basically, and we're going to the next step. If you remember from the sketch, we had a delay of 1 second between each clock pulse, and that's why we are actually pulsing the clock with a 1 second delay, and each second one value will be printed on the screen. So let's go back to sketch and change some stuff. So let's increment let's decrement first these timer to a smaller number. And also, if you remember, we had a parameter that we were passing to the step program counter. So what we could do, we could actually increase that to a bigger number. Let's say that we want to count up to 1024. And basically, we save the sketch, and then we're gonna check it, rerun or re-upload again, and I'm gonna clear the serial. And as you can see, now we're going much faster, and essentially we're reading and printing the values from the bus. So this is basically a basic test that you could see that we are counting in sequence. We're not skipping any values, and our counter is actually working as it's expected. Now, you could change that number to the maximum of 65,536, and it should be counting up to that number. Now, another thing is that we could actually set a value before we start the counting, and that's done through another function here, which we call it the set program counter. So let's have a look at this set program counter and see how we are actually setting a value into our program counter. So we have a function and it's called set program counter, and it gets a value as a parameter. And what we're basically doing here is, first thing, we are gonna set all the bus pins to output. And the reason being that we're trying to actually set a value from Arduino Mega. Therefore, from Arduino Mega's perspective, that should be an output, right? So we set the pins to output, and we talked about this function in previous videos. Then we're going to basically get that number and divide that number by 256, which means that it's going to give us the high byte value, decimal value of our basically parameter. So we're going to get actually the low bytes by dividing the same number, the value, by 256, and getting the remainder, whatever has been left after dividing by 256, will be our low byte. So now we get the high byte and the low byte as an integer number. And basically what we're doing here is that we're creating a mask bit, and we're going through the bus lines one by one, and we're basically doing a digital write on the bus lines, and we are doing an AND operation, or let's say a binary AND operation between the low byte and mask bit. And then on the next line, we're shifting the mask bit to the left by 1 so that we are ready to add the next bit basically in the sequence until we have all the bits set on the bus pins basically one by one. As you can see here, we're starting from the lowest bit and we're going to the highest bit, and basically we're just setting those pin one by one. If it's a low pin, we're going to set it low. If it's a high pin, we're going to set it high. So this is basically the output of this for loop here. Now, once the bus lines are set, now we're going to play with the control signals. As you can see, first, we are actually setting the inverted HI signal high. We set the HI signal itself low, and then we're going to basically bring the counter in signal high, and then we're going to pulse the clock. So that caused actually whatever is on the bus to be read by the chip and basically saved in our program counter chip. Now, once we have done that, then we have a short delay. Again, that delay is just to see the LEDs. And finally, what we're doing here is that we're just bringing the counter in signal low. Once we've done that, we are basically going to set the high bytes. Now, the high bytes is pretty much the same. The only difference is that now we are actually changing the HI signals, right? So now the inverted HI will be low and the HI itself will be high because we're trying to write on the high byte side of the circuit. The same thing, we're gonna basically set the count in or counter in high, and then we're gonna pulse the clock. And the end results is basically that we are setting both low byte and high bytes on our bus lines. All right. So remember that when we are setting the low byte, we are actually reading it into the chip, and then we're repeating the process. Now we're setting the high byte, and then we repeat the process and set it on the chip. And you see that the function here is that set bus pin input at the end, which basically we are reverting all the bus pins as an input type of pin, because we'll be actually reading from them from the main function. Now, that's really all about it in regard to setting a value. So if you go up here, you see that what we're doing here is that we are just resetting all the pins. We are setting the program counter to 1024, and then we start counting 1024 steps from that value. So let's just go a little bit slow here because we're, I guess, going too fast. So let's change that delay to, I don't know, 100 milliseconds, and let's just leave the clock at 10 milliseconds and see what we see. All right, so let's check that and upload that and bring up the screen and then clear it. So as you can see, we started this time from 1024 as our first value. So if I scroll back up, so that means that we are actually were successful in setting our program counter to an initial value of 1024. And as you can see, it will be counting for another 1024 steps. So essentially, if we wait enough, we're going to end up with 2048 as our final value in the count. So now with that, now if you look at the LEDs on an LED board, you notice that the HI signal is actually flashing on and off. So each time the HI signal is low, we are basically reading the low byte. And each time the HI signal is high and the LED comes up on the LED board, that means that we are actually reading the high bytes on the LED. So another thing that we actually could do here is to run the clock manually. So let's do that. Let's set the program counter at a specific number. Let's say we want to do 512. And then we're going to disable the step program counter because we're going to run the clock manually. So what I have done here is that in our function for the clock, you remember that we had a manual clock button. I wrote a function, and essentially what I'm doing, instead of just stepping the clock, I'm just calling that step counter, and I'm just stepping the counter by 1. So essentially, each time I press that button, the counter will be advanced by 1, and we're going to see the results on the screen. So that's another test that you could do. So let's do it. Let's just compile and upload the program again. I'm also going to clear the screen. And as you can see, we just executed the set value. And after that, the program just stopped. So let's actually press the manual clock and advance the clock, or basically call the read function or step function. All right, so if I press that, you see that the first value is 512 that we set. If we advance the clock, you see that with each call, you're actually reading just one value from and you see that sometimes it's actually jumping by 2, and the reason being is that that timer that we set for the clock is really low. We set it as, I believe, 10 milliseconds, so we could increase that to be basically 1 second interval between the clocks, so that way we have enough time to actually this is the bouncing effect that we have here on the switch. So let's do that. Let's just re-upload that, and let's bring it up. So we actually wrote the bytes into program counter, and now I'm gonna advance the clock. All right, so hopefully the sketch is clear, and as you can see, we can test basically all the values on our counter. The only thing is that you need to go back to that values, and let's say we want to count from 0. First set the program counter to 0, and then we're gonna, let's say, count to all the way up to the maximum counting, so 65,536. And let's just compile that. Also, let's reduce the time, because obviously you don't want to wait 1 second until you get into 65,000. So let's just reduce the delay to 1 millisecond, and maybe the clock pulse also 1 millisecond. Let's see what will happen. So let's upload that and bring up the counter. I'm gonna clear the screen, and I am not sure why it is not executing. So let's see, set the program counter to 0 and step program counter up to 65,530. Maybe we are exceeding the value for our integer, because that's an unsigned integer. So let's see. Yeah, it looks like we're exceeding our unsigned integer value by 1. So I guess that's a C programming thing. But again, as you can see, we are counting from 0. I mean, if you go back to the top of the screen, we started from 0 after setting the value of 0. And then we are actually counting all the way to 65,535. Now, I guess that concludes our testing here. I believe that's a good way of testing our program counter and see that actually it's working properly and it's outputting all the values on the bus. Basically that's it. So with that, I hope that you guys enjoyed this video. I'll catch up with you on our next video, which will be talking about our A and B registers. All right, stay tuned. See you there.